we come now to the energy eigenfunctions. So it turns out that because we do things by separation of variables, we can write the energy eigenfunctions as the product of a part that only depends on r and a part that depends on theta and phi only. This radial part, we call this the radial wave function. I can't spell function. Right? Depends just on r, as I said. And it turns out to also involve the two quantum numbers n and l. This, the angular part, YLM, these are something we call spherical harmonics. They turn out themselves to be the product of a part that goes only on theta and another part that depends only on phi. So you really do have this sort of three separate chunks. These spherical harmonics are inherently complex. They're a little tough to visualize, and we'll look at some visualizations in a second. So maybe the shapes of these they might be familiar from chemistry. Spherical harmonics turn out to be very useful anytime you're dealing with functions that you're trying to expand on a sphere. So in my research, where I'm talking about the scattering of light from a geometry that might be exactly spherical or at least sort of quasi-spherical, these functions and things derived from them turn out to be really, really essential. They're also really important in fields like astronomy, like planetary science and earth science. Anytime you want to sort of mathematically model sort of patterns of behavior over, let's say, the surface of the Earth, right? If you want to do something that's sort of analogous to a Fourier series, sort of like analogous to like expanding like the infinite standing wave on a string in terms of sines, it turns out that these functions are what you need to use. So I'm not going to go into detail now. Save that for 421 or math methods, but let me just say that these things are quite useful. If you go on in physics, you will definitely see a lot more of them. The spherical harmonics are tricky to visualize. So there are several things we can do. Well, because these wave functions are complex, we do typically look at the probability density. And the probability density, right, is going to just, as usual, be the modulus squared of psi NLM. And so I can write that too as a product of the modulus squared of the radial wave function times the modulus squared of the spherical harmonic YLM theta phi. So we're going to cut to my computer again. I'll show you some things that I have for trying to visualize these energy eigenfunctions, and then I'll say a couple more things about them. So one thing I just wanted to show you was this Falstad applet for viewing the hydrogen energy eigenfunctions. What we're looking at here is the probabilities, densities, sort of color, in sort of where the brightness gives you a sense of the scale, and then it turns out the color is going to tell us something about phase. Now we're now in n equals 1. This state is spherically symmetric, so if I just like rotate the coordinates around, nothing happens. Whoops, that's not what I wanted to do. There is an important takeaway, which is that, right, this is a state that is completely spherically symmetric.
This is not what the Bohr atom says, right? Because the Bohr atom says that we have an electron that's orbiting in a circular orbit. The electron, right, has a probability of being detected anywhere in sort of within this sort of spherically symmetric ball. It is definitely not restricted to orbiting in a plane. Now, when we get to some of the more interesting things, we again have a here's our here's our n equals 2, l equals 0 state. So the probability density sort of has a has a radial sort of minimum as you head out. So that turns out sort of having this extra node here turns out to be what happens at n equals 2, and you get more nodes as you go higher up. Things get fun when you look at the states that don't have L equals 0. These states have these lobes. So if I sort of try to align this on the z-axis here, something like that. And so again, this is you might have seen these sorts of diagrams as being associated with orbitals when you took chemistry. And again, notice that there's sort of a rotational symmetry about the z-axis here. Something that you might be able to see. So for this L equals 1, M equals 0, you can also look at what's different for, we sort of have lobes, we sort of have this, it ends up being like a donut shape if we have M equals 1, where the color, which sort of has to do with the phase, so now we're looking sort of down along the z-axis, the phase turns out to vary continuously going around here. So this is, again, it's a different way to visualize than what you had in your book, but that may be useful. So what we're showing you here is another way to visualize the angular part of the probability density for energy eigenfunctions. What we're plotting is the modulus squared of YLM theta phi. Now, what's a little bit tricky is that, right, what these plots are is they're using sort of radial distance from the origin as a measure of how big the how big YLM modulus squared is. So again, we see sort of spherical symmetry for the 0, 0 spherical harmonic, whereas for L equals 1, M equals 0, there's sort of an angular node at theta equals pi over 2, whereas for L equals 1, M equals plus or minus 1, there's an angular node at theta equals 0, and also on the other side of this at theta equals pi. Again, these sort of angular shapes, you might remember these as from chem as like the shape of your S and your P, D, and F orbitals in chemistry.
Now, it turns out that interpreting the probability density, and specifically thinking about the radial part of the probability density, turns out to be a little bit tricky, and I want to explain why here. What I'm going to say is a little bit different from what's in Knight, and I've got a handout on the on Sakai where I explain what's going on with Knight. But here's the deal. Right, so right in 1D, right, the probability of finding like a particle in a region dx was like psi squared times dx. The 3D generalization, right, so the prob of finding particle in some infinitesimal volume dV, right, ends up being psi n. So I'll just write this as the and we're assuming the particle is in an energy eigenfunction. Turns out to be the probability density times dV. Not too much of a surprise. And so the probability of finding a particle in some finite volume right, with the appropriate bounds turns out to be you've got to integrate this this probability density. So it's going to be some triple integral in general of psi n lm squared dv. Here's where things get tricky. What is the volume element in spherical coordinates? Element, let's write this. Right. It turns out to be, as hopefully you recall from multivariable calc, dv equals the following. It goes like dr, right? Not too surprising, times r d theta times r sine theta d phi. Oftentimes you might I've written it this way to because it helps to show where each piece comes from, but oftentimes we might get lazy and just write it all as r squared sine theta dr d theta d phi. Let me cut to my computer because I have something I want to show you to remind you of why the volume element looks like this in spherical.
So here's just a quick reminder of the volume element in spherical coordinates. Right, so the volume element is the volume of this sort of little box over here. Now sort of the thickness of this box is dr, so that's where the dr comes from. But we also need to know sort of the length of this side and the length of that side. Let's first deal with the length of this side here, which I think of as it lies along a line of longitude. And so longitude lines are like this. Now they have radius r, and sort of as we go down here, right, this sort of angle that I'm sort of subtending here, that angle is d theta. Because the longitude line has radius r, the length of this little segment here is r d theta. As for this, the length of this piece over here, these lie along sort of what I call latitude lines if we were to imagine a globe. Now the key thing is that the latitude lines, if you go and look on a globe, they have a radius of r sine theta. On a globe, right, that means that the latitude line, that's where the equator is a lot bigger than like near the north or the south pole. So you can go through the geometry, so like opposite over hypotenuse, and you can convince yourself that right this like latitude line has a radius r sine theta. So since the angle swept out sort of going this way is d phi, right, this little piece has a length of r sine theta d phi. All three of these combine then to give us our volume element, and as I wrote it on the board, I kind of prefer to think of it as dr times r d theta times r sine theta d phi.
So, because right, my volume element looks like this, the probability of finding my particle in some finite volume is going to be this kind of triple integral, where you would have to set the appropriate bounds over r, theta, and phi. However, because this this overall probability density, right, depends on a part that depends on just r and a part that depends on just theta and phi, what you end up doing is you can separate this out. So you have some, and you end up with an integral over r of, so I have r squared times my radial wave function, RNL of r, modulus squared dr, again with sort of appropriate bounds here, times, I'll just write this as a double integral over theta and phi, sine theta times y lm theta phi squared d theta d phi d. Yeah, so that I'm just sort of rewrite that d phi. There we are. Okay, so what we end up, right, defining is this radial probability density. So, which is the probability of finding the particle's radius between of finding the prob of finding r between r1 and r2. We define that that's going to be equal to this integral from r1 to r2 of r squared times r n l r squared d r. Now this almost looks like the same what we talked about with the probability density in 1D quantum mechanics, except that now this thing r squared r n l squared is what we call the radial probability density. The thing that we integrate over r to calculate the probability of finding my particle between radius r1 and radius r2. Again, we would have to also do the angular part of this if we wanted to sort of find the probability of the particle being within some finite volume.
Finally then, here's a slide of the radial part of the energy eigenfunctions and the radial probability density. So remember that when we take like the r squared into account for the probability density that we need to, even though the radial part of the wave function is peaked at r equals 0, that's not where the radial probability density peaks when we multiply by r squared. What you'll show on the homework is that this radial probability density for my n equals 1, l equals 0 state actually has a peak at r equals a Bohr, so right at the Bohr radius. You can see sort of how these look for the higher n and l states.
One quick word about normalization. So overall, the total probability of finding my electron everywhere in space has got to be 1, as we would expect. The way we normalize that is such that this kind of integral, when we set the bounds to be like from r equals 0 to infinity, theta to go from 0 to pi, and phi to go from 0 to 2 pi, we need this to be normalized to 1. Let me erase the board and I'll just write the normalization condition, just so that we're clear. Our overall normalization condition looks like this. This entire integral, this purple integral, has to equal 1. Conventionally, what we do is we sort of separately normalize each of these pieces. So conventionally, we end up defining the normalization prefactor in the radial wave function such that that by itself is normalized. So and also that the spherical harmonics are normalized, so that 1 equals 0 to pi sine theta y lm d theta d inside. The reason that I mention this is that Knight has a wacky normalization convention for the radial wave function that I've never seen anywhere else, where he does it differently by a factor of 4 pi. So again, look at the handout that I'm going to post for sort of the right way to normalize the radial wave function. So the last thing for today, let's look at a whiteboard exercise involving the radial probability density and the probability of finding the electron in the ground state, the n equals 1 state of hydrogen, inside the Bohr radius. So given the formula of the n equals 1, L equals 0 radial wave function I gave you, the probability of finding my particle to be at a radius smaller than the Bohr radius turns out to be given by the following integral. I want to find the probability that my particle is anywhere between r equals 0 and r equals a4. So that determines my limits of integration. I go from that integral sign is so wobbly. I go from 0 to a4, and then I integrate my radial probability density. I have r squared times my modulus squared of r and l. This happens to be real, so I have a factor of 2 over root a or cubed squared times the times by e to the other piece of this, e to the minus 2 r over a Bohr times dr. So that's the expression that we wanted. I wanted you to come up with in that last whiteboard exercise. Now it turns out this integral is doable. It requires sort of repeated integration by parts. I'll just tell you what the answer is. It turns out that this probability ends up being equal to, so 1 minus 5 over e squared, or about 0.323. So you can see a couple of things, right? There's a substantial probability for finding my electron inside the Bohr radius. There's also a substantial probability in this state of finding the electron outside the Bohr radius. One of the key takeaways is that, right, in the Schrodinger treatment of the hydrogen atom, it is not the case that the electron is going around in some orbit of a fixed radius. Rather, everything we know about the position of particles in general not being definite still carries over in the quantum mechanical treatment of hydrogen. So that was sort of a lightning tour of the Schrodinger model of the hydrogen atom. So this, again, is stuff you'll explore in more detail in 421. On Wednesday, I want to look at one more thing with the hydrogen atom, a surprising new property called spin. So we'll look at that, and then we'll probably start a little bit of like nuclear physics vocab, and that'll lead us into Friday. See you then.